Obviously, it cannot be a gas, right? Because if you compress the gas, the volume will go down. But the solids and the liquids, when you compress them, the volume will not change. It may change a little, but it is insignificant. And that is in thermodynamics, when we deal with liquids and solids, we usually approximate them as incompressible substances. Okay. And the specific volume is approximately constant. Let's say in the case of iron, okay. The specific heat of iron is 0.45 kilojoules per kilogram Kelvin, which means to raise the temperature of 1 kilogram iron by 1 degree C or 1 Kelvin. Last time we discussed they are the same thing, right? Because the size of 1 degree C is the same as the size of 1 Kelvin there. Is 0.45 kilojoules at room temperature. Now, in the case of solids and liquids, since the volume doesn't change almost at all, so we don't have the different specific heats like CV and CP as we did in the gases. So we just have one C, okay? And we just say the value of C is whatever. And to calculate the internal energy change, we simply use, now remember the general definition of CV was du partial derivative dt at constant V, but the V is already constant anyway, doesn't change. We can express this as du divided by dt, the regular differentials there, which means du is equal to C, and we get rid of the V also, C dt. Okay, so here it is, du is CV dt, which is C dt. Again, it doesn't change with pressure or volume, so it depends on temperature only, like ideal gases. Okay, and if you take the integral from 1 to 2, du becomes delta u, which is u2 minus u1, and in general C may depend on temperature, so integral from 1 to 2 CV dt. Special case if C is constant, okay, then C comes out of the integral sign, the constant value, and integral dt is simply from 1 to 2, T2 minus T1, right? So delta U is C average times delta T. For enthalpy changes, now remember the definition of enthalpy. H is equal to U plus PV. Okay. If you take the differential of this, differential of H is dH, differential of U is du. Now differential of PV, there are two terms here. So it is the differential of one times the other, and then you continue. So it is VdP plus PdV right here. Okay. But for incompressible substances, no change in volume, so it is 0. That means this term is 0. So we have this relation, du plus VdP for dH. If you substitute CV or C average dt for delta du, what you get is delta H is delta U plus V delta P, and approximately CV delta T plus V delta P. Okay. Now, for solids, Usually this term is insignificant, delta P. Okay. Therefore, when we deal with solids, we just say delta H, delta U are the same, and it is simply C delta T. Now, for liquids, let's consider two cases. If the pressure is constant for liquids, in that case, delta P will be constant, right? So in this relation, delta P will be, delta P will be 0 if P is constant. Delta P will be 0, so you have simply delta H is delta U, which is C delta T. So if the pressure is constant, then we just use this relation. If the temperature is constant, in that case, the first term will be 0. Delta T is 0. Then delta H will be V delta P. Okay. So these are the relations that we have. In the special case of incompressible substances. So if you have a solid, to summarize, delta H, delta U are the same, and it is C delta T. If you have a liquid, okay, you look at the process. If let's say it is constant temperature, it is simply V delta P. We use this in pump work a lot, calculating the pump work. And if the pressure is constant, then delta H and delta U are simply C delta T. I'll show you some examples. Okay, now let's do some examples. Let's say we have an iron block, as you see here. Okay, it is 50 kilogram. The mass is given. The temperature is 80 degrees. It is dropped into an insulated tank. So if the tank is insulated, what does it mean? What is 0? Anybody?
Temperature difference.
Heat transfer, right? If it is insulated, then we cannot have any heat transfer in or out. So Q is 0. And do you see any shaft electrical wires entering or any volume change here, like a piston-cylinder device? No. Therefore, we can say the work is also 0 here. Okay. So we also do some observations as we read. So it says, insulated tank. It contains 0.5 cubic meters of liquid water at a temperature of 25. And what is the question? When thermal equilibrium is reached, that is, iron transfers the heat to the water as its temperature drops from 80 degrees to whatever, because it will not be 25 because water will be heated, right? It is absorbing all that heat. There will be something in between 25 and 80. What is that common temperature? So what is T final? Okay, this is the question. Okay, now one is liquid, the other solid. So we can say both are incompressible. And look at the temperatures, 80 degrees to 25 degrees. So we can just use a constant specific heats at room temperature for both of them. And there is no mention of movement, so kinetic and potential energies, we can safely assume it is 0. Okay. And we don't see any electrical shaft or other forms of work involved. So the work is 0. And the system is well insulated. Okay. By this, we take the system as the iron plus the water. That is, the inner surface of the tank is the system boundary. Okay, right here. The inner surface of the tank, whatever is in the tank, which is water and iron. Okay. So we make sure that we understand the problem. And then energy balance. Obviously, what will happen here physically? Some energy, heat, will be transferred from iron to water. Okay, the temperature will drop, and the temperature of water will increase because it is receiving this thermal energy here. Okay, for the combined system. Okay, the iron plus water, the combined system. Energy in, energy out. There is no energy entering. So this is the system boundary here. Okay, no energy is crossing in either direction. Okay, it is well insulated, and there are no work interactions. Therefore, this is zero. This is zero. So it is zero, and no kinetic and potential energy involved. So delta E is delta U. So this is the energy balance. Okay, which means the internal energy of the system, which is iron plus water, will remain constant. Why? Because there is no energy entering or leaving this combined system there. Okay, so delta U system, since we have two distinct components here, iron and water, the total internal energy change of a system is the internal change of the components summed together. Okay, so the sum of delta U iron and delta U water. Okay, if you add them up, it will be delta U of the total. But delta U is for incompressible substances C delta T, right? Therefore, we can write it as MC T2 minus T1 iron, and then MC T2 minus T1 water. Okay, one of them will be positive, the other one will be negative. And what is known here? Okay, the volume of water is given, which means I can calculate the mass, and then the specific heats I can get from tables. T1s are given. What is left? T2. And this T2, they are equal to each other, because it is the common temperature. We have thermal equilibrium. Okay. Okay, so here is the equation. Now, what is the mass of water? Mass is total volume divided by specific volume. And for water, it is 0.001. We can always use it. So this is the mass of water. And then in this equation here, plug in the values. Okay, for iron, mass is 50 kilogram, specific heat 0.45. T2 we don't know, just leave it there. T1 iron is 80. For water, mass is 500, specific heat 4.18, initial temperature 25. T2 we don't know, we just leave it, but it is the same T2. Okay, so T2 iron is equal to T2 water. Okay, so we have one unknown there, and you can solve it. When you do, you get 25.6 degrees. So the result is after the iron and water, they reach the same temperature. There is no temperature difference. That common temperature is 25.6 degrees C, based on the conservation of energy principle. Okay. Now, any questions on this example?
From there, can we find the iron's volume?
You can find the iron's volume. What you do is you go to the same table, okay, from this relation here. You can say mass is rho times V, okay, and what is given? The mass of the iron. This rho density you can get from table for the iron. It should be like 7,800 or something. And then you can calculate the volume of the iron. So this relation is valid for anything. If you know volume and the density or specific volume, okay, because keep in mind that always density is 1 over specific volume. So if you know one, you can always calculate the other. Density is kilograms per cubic meter, and specific volume is cubic meter per kilogram. So you simply take the inverse of it. Okay, other questions? No questions. Okay. Now let's go through another example, which is more challenging. Okay, in industry, we often have, steel rods continually being heated or cooled in long furnaces. Okay, so in this case, we have aluminum rods, as you see here. This is aluminum here, and there is a long oven at 700 degrees, and it is moving at a speed of 7 meters per minute. Now this means here you have probably liquid aluminum, and then you force it through some section, okay, at this diameter, and it cools and solidifies. No, in this case, you don't do that. It is a reverse process. Okay, you have this long aluminum rod at room temperature, and you want to heat it to 400 degrees. Okay, but you feed it continually. It can be a long one, or simply when one ends, you simply start the other rod there. The question is, what is the rate of heat transfer to the rods? Now, initially it is at 20 degrees, and when it leaves at 400 degrees. How can that happen? Obviously, heat must enter the aluminum in the oven, in the furnace here, right? Now, the question is, how much heat transfer is happening? It is important because that means if the oven temperature is to remain constant at this value, we will have to, burn maybe like natural gas continually, so that heat is replenished there. Okay. So this time we take this aluminum rod, the part in the oven, okay, as the system. Okay, we can solve it as a control volume problem, but let's do it as a closed system. Now, what we will do is, now we know that if you take a rod like this, which is 8 meters long, okay, it takes 1 minute for the temperature to go from 20 to 400. Okay, so what we can do is we can determine how much heat is needed to raise the temperature of 8 meter long rod. And once we determine that amount, okay, we know that it is the heat transfer in 1 minute. Then if we divide it by 1 minute, it will give us a heat transfer rate per minute. Okay. So this is the system. And for that system, we will do the energy balance. What is the energy balance? Always energy in minus energy out is energy change of the system. And the system is this 8 meter section of the aluminum rod. Okay, what is energy entering here? Only we have heat entering, heat in. There is no heat loss from there. And there is no work involved. So heat in. And no kinetic potential energies involved, okay? So it is, instead of delta E, delta U, and it is solid, Okay, so delta U is mu2 minus u1, and I can just say it is mc delta t. Okay, because delta U is c delta t there. So by applying the energy balance, I get this relation. That is, the amount of heat transfer is the mass of aluminum times specific heat times delta T. Now, T1 initial temperature is 20, T2 is 400, C I can get from table, and then mass. And mass is simply the mass of this rod. If I can calculate the volume and then the mass. If I put them together, you can see that I can simply get the result very easily. And then I can divide the result by delta T, which is 1 minute. Because in 1 minute, I have this 8-meter section heated from 20 to 400. And it will give me the heat transfer rate. Okay, so this is the relation. Okay. Now, what is mass? Density times volume. And what is the volume of a cylinder? Pi diameter square over 4 times length. So this is the from the table at the end of the book. I think table, it may be like 1 or 2, whatever. I can get the density. In fact, I can get both the specific heat and the density from there. The diameter is 5 centimeters, so I convert it to meter because this is in meter. And the length is 8 meters. See, everything is in meter, which will make my job easy. Okay, so cubic meters will cancel. I will get 42.41 kilogram for the mass of the aluminum block there. And if you plug in the values into this relation, okay, the mass, specific heat, delta T, you end up with 15,680 kilojoules. This is for 8-meter section, which means during 1 minute. Because in 1 minute, 8-meter section is heated from 20 to 400. Okay, and then if you divide this by time and delta T, it is 1 minute. So this divided by, 1 is again 15,680 kilojoules per minute. If you want it in second, divide that also by 60. Okay, you get 261 kilojoules per second. Now, if you don't feel comfortable with this and you want to do things in the rate form, you can also do that. Now, M is rho times V, right? Divide by delta T, this relation. The left side will become mass flow rate. Okay. And the right side, the volume will become volume flow rate. The density doesn't change. Now, that means mass flow per unit time, volume flow per unit time. Okay, what is the volume? This is the volume. Divide by delta T, okay? But what is this length divided by delta T? It is velocity, okay? Therefore, the relation becomes rho pi d square over 4 times velocity, which is given to be 8 meters per minute. So you can do it directly that way and you get the same result there. Okay? Any questions on this example? Okay, which one is easier? The first way. Let's say this is first way and this is the second way. Anybody?
I think the first way is easier because when it's come to mass flow rate, it confused me.
Okay. It is what I thought, so I did that one in detail first, but I also gave the alternative there. And the reason I also included the details here is that you can kind of build confidence, saying that working with rate forms is not really complicated. In fact, it is easier. Okay. So make sure that, you know, in your mind, you combine the two methods. Why, let's say this is volume times, the cross-sectional area times velocity, whereas the other one is cross-sectional area times length. And then later on, we divide by, you know, delta t here. Kind of combine those in your mind. Okay, any other questions? Okay, no question. So let me go back and go through the example in the ideal gas. Okay. And this will also refresh your memory. Okay, this is example 10 in the textbook. Now, here we have a piston cylinder device. Initially contains air at given pressure and temperature. Okay. At this state, we have this piston. It is sitting on top of two stops, as you see here. So it cannot fall. There are stops there. And the mass of the piston is such that a 350 kilopascal pressure is required to move it. And now initially the pressure inside is 150, which means because of these stops right here, the piston cannot fall, but it is exerting a force on the stops because it is heavy. So we need 350 to lift it. Now we transfer heat, as you see here. As air is heated at constant volume, what will happen to temperature? From ideal gas relation, PV is RT, right? If V is constant, and if, let's say, you are adding heat, the temperature will rise, which means the pressure also will rise until the pressure rises to what value? From 150 to 350. Okay. And when the pressure rises to 350 kilopascal, what will happen to the piston? It will start going up. Okay, because if it doesn't, then the pressure next will be like 351, which is higher than the pressure needed to raise it. Okay, so it will have to go up because now there is a net force exerted by air, okay, to the piston there. So it will have to go up. Then the process ends when the volume doubles. So initial volume is 0.4 cubic meter. That means the final volume is 0.8 cubic meters. And the question is, what is the final temperature? What is the work done by air as it is expanding? And what is the total heat transferred to the air? So what is this Q here? Okay. Is the question clear?
Yes, it's clear.
Yes.
Okay. Okay. Now these are the details as to, you know, what how the thinking process should be occurring in your mind. So I suggest that you read these carefully. Okay. That way, you know, you develop the right approach in your mind. But you should go through this thinking here. For example, this is, you make sure that you understand the problem. What is given, what is happening, and what is to be found. And in engineering, we always use assumptions, but we make sure that they are logical and reasonable. Let's say the first assumption says the air is an ideal gas. Look at the temperature, 27 degrees, and even if it goes up a few hundred degrees, doesn't matter. In fact, it will be even better. So the air at temperatures of, in fact, really any temperature, unless the pressure is extremely high, like, you know, many megapascals, air is an ideal gas based on experience. Therefore, you look at the pressure here, 1.5 atmosphere, and then 3.5 atmosphere. Oh, this is peanuts for air. It is nothing. Therefore, air is an ideal gas. And you can also check with the critical point of, let's say, oxygen or nitrogen or the air there directly, which is some kind of average. And the system is stationary, therefore there is no change of kinetic potential energies. Okay, we don't need to deal with that. So they are 0, as you see here. Therefore, delta E is delta U. Now the volume. The volume remains constant until the piston starts to move, and then the pressure remains constant until the end of the process. So initially, on a PV diagram, it helps to plot the PV diagram. Initially, the volume remains constant, and on a PV diagram, any constant volume process is a vertical line, right? Because anywhere on this line, okay, the value of volume is the same. Write that value there. Okay, so constant volume, you go up. The pressure rises until you reach 350, and then the pressure remains constant, and any constant pressure process on a PV diagram will have to be horizontal like this. Here the pressure is constant, okay, and the volume is increasing as the piston moves up. So this is the process curve like this until the volume doubles. So this is where the process ends. Okay, so do we have boundary work here? Anybody? Okay, Tuna.
Yes, sir.
Tuna, what do you think? Do we have boundary work here?
I think yes, sir.
Yes. Are you sure?
No, I can't explain that. Yes.
Okay. Well, you can just say that on a PV diagram, if there is an area under the process curve, okay,
Yes.
which is this
Yes.
dark area here, that area corresponds to what?
Work.
Boundary work, right?
Yes.
But if the process ended at 2, okay, then there would be no boundary work because under the line there is no area. The volume is constant. It is a PDV work, boundary work. Obviously, dV is the change in volume is 0. Okay. So let's do the easy part first. The first question is the temperature. It's an ideal gas. So for an ideal gas, okay, of constant mass, here the mass is constant, okay. Then what is the relation we have? P1 V1 is mRT1, right? And then P2 V2, the final state. In fact, let's make it P3 V3, mRT3. Take the ratio. MRs will cancel. Rearrange it. You will get this relation. Okay. And you don't need to plug in the value of V1. The first volume is V1. The second one is 2V1. If you want, you can also plug in numbers, but they will cancel anyway. Here, T3 is the only unknown, but make sure that you express the pressure in Kelvin, okay? As you see here, it has to be Kelvin, okay? And if you solve for T3, you get 1400, okay? Now, the boundary work, you can simply find the area, okay, which is delta V, okay, the area. This is delta V, okay, and this is P2. So it goes from 0 because we find the total work. So this is P2, which is same as P3. Okay. So P2 is 350 kilopascal, and delta V is V2 minus V1, which is 0.4. It is 140 cubic meter kilopascal, and we know that cubic meter kilopascal is equivalent to kilojoule. So here is the work done. Okay. And how can you find the heat transfer? Using the energy balance. Okay, let's do this in this bigger picture here. Now look at here. Again, it's a closed system. There is no mass entering or leaving during process. So it is simply energy in minus energy out is energy change. Okay. And now what is energy entering? We have heat entering, right? So Q in, and then the system is doing work, boundary work. Energy out, pushing the air out and raising the piston. So minus boundary work out. No other energy entering or leaving. Stationary system, so delta E is delta U, which is mass times U3 minus U1. So the final internal energy minus the initial internal energy, U1. Okay. So this is where we are. Okay, mass, let's find the mass. We need the mass. Okay, using the ideal gas relation, just plug in the values. And then U values, we go to air table, table 17. Okay, and at 300 Kelvin, this is what we read for U. At 1400, this is what we read for the final U. If you plug in the values, here is the mass, U3, U1, and here is the boundary work. This is the only unknown Qn. And when you solve for it, you get the amount of heat transfer there. Which means during this process, 767 kilojoules of heat is transferred to the air. And the work done is 140. Okay, a question. First of all, do we have any questions so far? No question. Okay, then let me ask you a question. Okay, is Cem Mert there? Cem?
Yes, sir, I'm here.
Okay, my question is to you.
Okay.
Okay, now the total work done by the air is 140 kilojoules, right?
Yes.
Now this work is used to push the atmosphere out and to raise the piston. It is a heavy piston, right?
Yes, of course.
How would you calculate the work done against the atmosphere? That is to push this atmospheric air out of the way as the piston rises.
Can we use volume of that?
Yes, you can, which is the same as the volume change of the cylinder, right? Because it is how much the air is pushed out. It is the volume swept by the piston here. Okay, yeah, you can use that volume change. What else would you need?
I can use a constant for air.
Constant?
For calculations. Yes, constant.
Constant pressure, you mean?
Maybe constant kilogram, constant mass, maybe.
No, there is no change there. That is the mass of areas. If you mean this one, it is constant anyway. And the mass of the atmosphere outside, it is also constant. So look at this relation here. Now keep in mind that boundary work is integral PdV, right? And if let's say you take the atmospheric air as the system, okay, atmospheric air, does it change during this process? as the piston goes up? Will the pressure of the air outside change?
No.
No, which means
Okay.
constant. So let's call it P0. Okay, so this will be the atmospheric work. P0 times delta V, which is the same as delta V of the system, right? And what is the value of P0, atmospheric pressure? 1 atmosphere? Yes, which is about 100 kilopascal. Okay, times delta V is 0.4, right? 0.4 cubic meter. So what is the result? 40 kilopascal cubic meter, which is 40 kilojoules. Which means of the 140 kilojoules, okay, 40 kilojoule of work is done just to push the atmospheric air out. Now, what is left there? 100 kilojoules. Now, Mustafa, are you there?
Yes, I'm here.
Okay, where is that 100 kilojoules of energy now? Now, obviously, you know, we did 140 kilojoule of work. Okay, 40 kilojoule is used to push the atmosphere out of the way. Okay, so it is transferred to the atmosphere. How about the 100 kilojoule? Where is it now?
I was about to ask to you that.
Okay, so let's get help from maybe Ahmed. Ahmed, what do you think? Is Ahmed there?
I have an idea, sir.
Okay, Adam? Is Adam there? Abdul Karim? I think Adam is not there, huh?
Yes, sir.
Oh, you are there?
No, I mean he's not there.
Okay, he is not there. Anyone? Any volunteer?
I can.
Okay.
The 100 joule goes for the piston as potential energy.
Excellent. Exactly. So it's a heavy piston, right? And obviously you are raising the piston. It is going up. Okay. So as it goes up, its potential energy is going up. So depending on the mass and the amount of distance traveled there, the elevation height. Okay. Right now, the piston has 100 kilojoules more energy. So if let's say the piston were to drop back to this level, the stops, its potential energy would go down by 100 kilojoules. Now you can argue that as air expands, part of the air is now at a higher location, so it has more potential energy, but it is very, very small compared to the piston there. So we can just say it is the whole thing is to the piston. Okay, so let's stop here and take a 5-minute break. After the break, we will start the new chapter.